and welcome to this video looking at the Hardy-Weinberg Principle. It was developed by mathematicians, and it is used to look at allele frequencies and genotypes within populations. It can be used to find out how many heterozygous individuals there are for a particular trait. And we're going to look at the key assumptions made by the principle. So it assumes that the population is large enough to make sampling errors negligible. So we need to have a large sample, and that's to make sampling errors negligible. Okay, and then it needs to be mating within the population occurs at random, so it has to be random mating. In other words, it can't be like in an artificial environment. We can't be using artificial selection. It's got to be random mating. It assumes that there is no mutation, migration or genetic drift going on. No migration, no mutation or genetic drift. It assumes that there is no selective advantage for any genotype, so there's no selection. So there's no selection pressure really is what it's saying for any particular characteristic. I'm going to go through this as a worked example, I think. I'm going to take these off so I've got a bit more space on the board. Right, so the equation that we use for this is that p squared plus 2pq plus q squared equals 1, and that p plus q equals 1. And what we mean by this is Q is the recessive allele and P is the dominant allele. So Q is recessive and P is dominant. So when we're saying Q squared, it just means QQ. So recessive and recessive, it means homozygous recessive. This means homozygous dominant, and this is the heterozygous. And that is all adding up to 1. So you're either homozygous dominant, homozygous recessive, or heterozygous. There's no other possibilities, so that equals 1. And heterozygous, recessive and dominant equals 1. There's no other allele other than recessive and dominant, so it equals 1. So what we can use this to find then is if we were told that if we can estimate the frequency of a recessive allele in the population. So if we're looking at example, say that cystic fibrosis is a recessive disorder and it affects 1 in every 400 people. Okay, so we know that this is recessive, so we know that Q squared must equal 1 out of 400. So if we know that, then we can know what Q equals, because we can square root this. So Q equals the square root of 1 over 400. And that equals 0.05. And then we also know from this equation, we can substitute this into this equation, we can find what P equals. P equals 1 minus Q if we rearrange that. So P equals 1 minus 0.05. P equals 0.95. And then what we can do, say if the question was asking us to calculate the frequency of people that were heterozygous or carriers, then we can find out this by putting it into this to find 2pq. So 2pq equals 2 times p times q. So 2pq would equal 2 times p, which we know to be 0.95, times q, which is 0.05. And that 2pq equals 0.095. So that's what 2pq equals. And then if we wanted to find the number of actual individuals in this population that's been mentioned, so in every 400, then we can do 0.095 times by 400 to see how many individuals in this population were carriers for cystic fibrosis. We could do this and that equals 38. So there's 38 individuals that are heterozygous. Or we could work out a percentage by timesing it by 100. Okay? So that'd be 9.5% are heterozygous. So that is how you find this out, and that's how we use it. That is everything for this video. Thank you for watching.